Welcome back. So this is the answer for the second example. Please compare this with what you get here for this example. And these terms are still listed in order. For example, the 1 over x to the 6 here is corresponding to the first term, and all we need to do here is really just to simplify them. And the negative 160 was the term we mentioned earlier, sitting right here. Okay? All right. Another quite interesting application of the binomial formula I would like to introduce is the third example here. Let's try to prove the identity that 2 to the n is always equal to the sum of the binomial numbers n choose 0 plus n choose 1 all the way to n choose n for any natural number n. Okay. Before this section, what would be the first method that comes to us to prove this? The idea would be, if we want to prove an identity involving any natural number n, the natural idea would be principle of mathematical induction. And indeed, that works. Okay, you can try to prove that by principle of mathematical induction on n. You need to verify the initial case, and then assume an induction hypothesis, assume that the identity is working as true for n is equal to k, and then try to prove this identity where n is equal to k plus 1. Okay, that definitely works, but it is going to take a little bit longer time than the following method I will show you. Okay. So here is the proof we can provide with the binomial formula. If we consider the nth power of 1 plus 1, and we can definitely follow this out by considering this 1 as the first quantity, which was the x mentioned in our binomial theorem, and this other one as the y term. Okay. So if we expand this, the binomial theorem says this is a sum where k equals to 0 all the way to n of n choose k times x, which is the first quantity, 1 here, to the power of k, times y, which is again 1, to the power of n minus k. The key is any powers of 1 would be just 1. So these two terms are both 1s. 1 times 1 is still 1. Altogether, these will be 1, no matter what's the value of k and what is the value of n. Therefore, the right-hand side can be really just expanded by plugging k values into this coefficient here. And for start, we have n choose 0. And then second, we have n choose 1. And n choose 2, and so on. Oops. Okay. The last term we have in the sum is n choose n. So this is a much easier, a much quick proof on the identity. Okay. Of course, I started from 1 plus 1 to the n because that is also 2 to the n. That's the end of the proof of this identity. Isn't that just convenient? The point of this example is to point out that to use the binomial theorem, we've seen that the first quantity here is a term of x, the second here is a term of y, and they could be a mixture of x, y's, or they could be both terms of x. And here in this example, they could be both just numbers. Okay, they could be any quantity as long as you have an expression in the form of something plus some other stuff. This is supposed to be a banana. to the power of n, you can always use the binomial theorem. Okay? Alright, for the homework of this section, we have number 3, part A and C, number 5, part A, B, and D. Thank you for watching.